Hello everyone, my name is Pita Vaouli and we are the Electrical Engineering Instrumentation team for the Battery Workforce Challenge here at California State University of Los Angeles. Our team's role in this competition is focused on modeling, documenting, and preparing the electrical side of the battery pack, specifically the systems that make the battery safe, reliable, and ready for vehicle integration. Over these past 2 semesters, we've been laying the foundation for the battery's behavior, both in software and in the documentation required for hardware development. Today, our team is going to walk you through the progress we've made and how our work sets up next year's teams for the full build phase. This is our electrical engineering instrumentation team. Jaime, Luis, Carlos, myself, and Thomas. What made our group effective is that each of us brought a different technical strength. Some members are more focused on software modeling, others are stronger in hardware analysis and documentation. And together, we were able to balance the wide range of responsibilities required by the competition. As the project progressed and the deliverables became more complex, those differences allowed us to divide tasks efficiently and maintain steady progress across both semesters. And that collaboration is what set the tone for our work. We started by developing a shared understanding of the entire battery system and used that foundation to build the models and documentation you'll see throughout this presentation. The Battery Workforce Challenge is a 3-year national competition where universities design, model, and eventually build a fully functioning electric vehicle battery pack. California State Los Angeles competes as the Charging Eagles team, and we are currently in year 2 of the competition. This year focuses heavily on subsystem development, meaning the electrical, mechanical, thermal, and software teams all work in parallel to prepare the battery pack for its build phase next year. Instead of assembling hardware at this stage, the emphasis is on understanding the battery's behavior and creating the models and documentation required to meet strict engineering deliverables. These deliverables follow real industry expectations, which is why this project feels much more like an engineering program than a typical class assignment. And with that structure in mind, our team's role becomes clear. We were responsible for laying down the electrical foundation that the next team will use when the actual build begins. To understand the work we did in the first semester, we first need to understand the system we're modeling. This diagram shows the battery management system architecture, essentially the brain of the entire pack. The BMS constantly monitors every critical part of the battery: voltage from each cell group, current from the Hall effect sensor, and temperatures from multiple thermistors placed throughout the module. All of that information flows into the M450 ECU, which processes safety logic in real time. The ECU then decides whether the battery is in a safe state to operate, whether the contactors should open or close, and whether a fault needs to be communicated to the rest of the vehicle through CAN. What's important here is how interconnected everything is. A small change in temperature or isolation can trigger a whole sequence of actions. So the software that controls this system has to be extremely reliable. This architecture became the blueprint for all of our modeling work. Every input and output shown here eventually became its own subsystem in Simulink or Stateflow. And because we didn't have the hardware yet, this high-level map guided us through building a digital version of the battery's behavior that could later be matched to the physical components.
To program the M450 ECU, we are using MATLAB with the Open ECU compiler. Within MATLAB, we are using the Simulink visual programming language. To implement state machines, Stateflow is used. Simulink test will be used to perform unit tests and confirm functionality before interfacing with the battery hardware. Hi everyone, I'm Thomas from the Software Instrumentation team. Starting here with the power up and power down subsystem, this slide shows the requirements that are specified in the Battery Workforce Challenge software requirements document. These requirements drove the design that will be shown in a high-level flowchart. When the pack is powered up, the software first engages a pre-charge resistor to limit the inrush current to below 50 amps. The software then monitors the DC link voltage until it reaches 90% of the pack voltage. This process takes less than 2 seconds. During this process, if any check fails, the software halts and reports the fault. On shutdown, the main contactor opens in under 50 milliseconds, and the remaining voltage bleeds below 10 volts within 5 seconds. Throughout both sequences, the code broadcasts status and diagnostic messages on the CAN bus every 20 milliseconds. This ensures the vehicle always has real-time visibility into the current BPCM status. On the left, we have a simplified flowchart of the power-up function. The process of this function begins when the 12-volt wake-up signal is asserted. First, the presence of a valid high-voltage interlock or HVIL loop is confirmed. If we don't have a valid HVIL signal, then we immediately flag the fault and halt the sequence. If HVIL passes, the BPCM checks for other faults and closes the pre-charge contactor if none are found. If faults are found, then they're immediately reported and the process stops. From there, the software waits for the pre-charge phase to complete. Once the DC link voltage reaches 95% of the pack voltage, then the main contactor closes. The status signals are transmitted and the power on sequence is complete. Now, if we're going from a powered up state, we follow the powered down process shown on the right. First, we check if the contactor is closed. If it's not, we cancel the shutdown because we're not in the expected state. If the contactor is closed, then we open the contactor and send status signals. If we're still receiving the power down signal, then we continue with disabling the LOC diagnostics, shutting down the comms, and initiating the pre-power down actions. Then the power down is complete. This slide shows how Stellantis' block diagram requirement was achieved by translating the detailed flowchart into a software-friendly diagram for Simulink. First, each step of the original power-up, power-down flowchart, wake-up and initialization, pre-charge sequencer, main contactor closure, fault monitor, and controlled shutdown were represented as individual functional blocks. Then clear input and output ports for each block were defined to match the RTE style interface that Stellantis specified. Sensor and CAN inputs on the left, contactor command and diagnostic outputs on the right. Next, those blocks were connected together in the same left to right sequence as the flowchart. The wake-up block feeds a wake-up command into the contactor control, which in turn drives the pre-charge and main contactor blocks. Simultaneously, the fault monitor block runs in parallel and can override any stage with a shutdown command. Finally, the power down block gracefully de-energizes the system when the EVCU shutdown signal arrives. With that, the block diagram is complete, and it was imported into Simulink and hooked up to test bench stimuli. A rising SOC and hardware wake signal kicked off the startup. Intentional fault flags to trigger the fault path and an EVCU shutdown pulse were supplied. By running the model, it was verified that each block produced the correct contactor commands, issued system ready and system shutdown CAN messages, and logged diagnostics at exactly the right moments. This end-to-end simulation gave confidence that the software logic was correct and will work with operation and fault scenarios. This will be confirmed with future hardware in the loop testing. On this slide, you can see how the abstract power-up logic was translated into a working Simulink model for preliminary testing. The first screenshot shows a top-level Simulink layout. Each stage of the power-up sequence was encapsulated: wake-up condition, HVIL check, initialization, CAN ready, status transmission, and contactor closure as individual function blocks wired in series. Each box emits a Boolean flag once its criteria are met, and that flag drives the next block in the chain. In the second screenshot, this shows the state flow chart for the first stage. This models the simple two-state logic: signal on when wake up is greater than 1, and signal off when wake up is less than 1. Those transitions are executed exactly as they should in response to the input signal. This gives confidence that the state machine matches the block diagram requirements. The third screenshot shows the scope output from a 10-second run. You can see the signal step from 0 to 1 almost immediately after the time 0. This proves that the chart is successfully propagating the power-up command through the model. As of today, this is where we stand, and we will kick off with hardware in the loop testing soon that will prove these functions work correctly with the actual battery hardware. The high voltage interlock, abbreviated as HVIL, is part of the vehicle safety system that will deactivate the high voltage output from the battery if an electrical, physical, or vehicle fault occurs. The HVIL signal is an alternating high and low square wave signal that is daisy chained from component to component. If any component in the chain senses a fault or is physically disconnected, the signal is deasserted. The runtime environment, consisting of the vehicle control modules and devices on the CAN bus network, provide inputs on vehicle status and the HVIL signal. The HVIL system monitors the shutdown status, sensor inputs, and the HVIL input. If the inputs are acceptable, the HVIL system energizes the HVIL output and sends the required CAN commands. If the input falls outside the allowable values or the HVIL input is de-energized, the HVIL output is deasserted and the CAN status is sent. The block diagram was converted into a simplified flowchart shown here. At the start, we first check if HVIL input is valid. If it is, we then check if we've received a shutdown signal. If we have not, then we check for any faults that could have been detected. If no faults are detected, we send the CAN status and we assert the HVIL output. The process then returns to the beginning and continues again. If at any point we don't have valid HVIL, a shutdown signal is received, or a fault is detected, HVIL is deasserted, and the status messages are sent. To implement the functionality of the flowchart, a Simulink HVIL module was created. Inside there, a state flow diagram describes the different states, the criteria for transition between states, and the functions that occur at that time. As you can see, we start off in the HVIL de-energized state. If all the requirements are satisfied, we transition to the HVIL energized state. Immediately when we get into the HVIL energized state, we then move into an HVIL high OK. This is when the input for the HVIL is at a high level. We basically need to check that nothing has failed at this point and that we switch quickly enough. If we don't switch quickly enough to the HVIL low state, then we end up back at the HVIL de-energized state, and then we begin checking again to see if we should energize HVIL. This is not fully implemented at this time, but this gives a rough idea of the functionality of the HVIL system. Moving forward from the Simulink and state flow tests shown here, we will proceed with hardware in the loop testing. This will first take place as a benchtop test with low voltage stand-ins. This testing is safe and can prove the functionality. This will be followed by full end-to-end testing with the full battery pack and high voltage lines.
A key software and safety requirement which our team has been developing in accordance to the Battery Workhorse Challenge software documents is the loss of isolation detection function. The purpose of the loss of isolation detection function, or LOI, is to ensure the high voltage electrical system in an electric vehicle remains safely isolated from the chassis and low voltage circuits. This prevents shock hazards and ensures regulatory compliance. Here we have the software block diagram for the LOI function. This allows us to visualize the input and output signal management of the overall function. As seen here, LOI expects 4 levels of inputs and outputs a total of 3 CAN signals. Moving forward, we have the software flowchart. This takes the LOI software requirements provided by Stellantis and displays them in a visually understandable flow of logic using blocks. This is a vital step in the software implementation process, as it allows us to organize the logic implementation of the overall software function in MATLAB Simulink and Stateflow. Here we are able to see a proper display of conditional statements functional signal logic and expected signal outputs. This function takes into account high voltage isolation status, high voltage interlock status, isolation resistance levels, and the status of end of year completion tests. Moving on from the software flowchart, we have our MATLAB Simulink implementation of the LOI software logic. Here, we took the logic outlined in our flowchart and implemented it in MATLAB. To be specific, we are using Simulink and stateful logic diagrams to apply our logic. Our function model is built on Boolean logic to process input data. Here, we take HVO abort condition are measured and positive contact to high voltage, and the LOI system uses stateful logic to assess whether the system will output pass, fail, or in progress signals. As can be seen above, we began to experiment using OpenECU blocks to transmit canned messages. This is one of the building blocks that will eventually allow us to run this model on the M450 microcontroller. Building onto this, we began the process of creating test cases to analyze our reliability of our code. The goal of this is to ensure the input and output logic of our code is up to requirements before moving on to the testing with the M450 microcontroller.
To begin semester 2, we reorganized our team into two subgroups, the hardware support team and the software instrumentation team. This restructuring wasn't random. It was based directly on the Battery Workforce Challenge Year 3 deliverable expectations, which require teams to shift from conceptual planning into concrete development of a functioning battery module. The hardware support team included Pita, Jaime, and myself. Our responsibility was anything related to the physical construction of the module. That included researching and selecting connectors, determining protection components, laying out the wiring architecture, and building the documentation that manufacturers and inspectors will eventually rely on. On the other side, the software instrumentation team included Luis and Thomas. Their work focused primarily on data acquisition, sensor calibration, and CAN-based instrumentation. They ensured that every physical component the hardware team selected could be measured, logged, and integrated into the vehicle's diagnostic system. This split allowed both groups to work in parallel. Instead of waiting for the hardware to be finished before software could begin, both sides made progress at the same time. This was especially important because Year 3 deliverables, such as HG1 and HG2, depend on tight integration between wiring, sensors, and BMS interface. So, overall, reorganizing into these two focused teams made us more efficient, prevented delays, and made our workflow much closer to what an actual industry EV battery team looks like. As the hardware support team, our responsibilities in semester 2 focused on the electrical portions of HG1 and HG2 and producing all electrical content for the build book. The build book is the full manufacturing instruction set for the battery module, so our documentation had to match the mechanical and software's work. We met regularly with the mechanical to review progress, verify compatibility, and make sure our electrical components supported their physical design. The specific electrical deliverables we were responsible for included ensuring the CSC and sense line fuses were located inside the module, selecting connectors and interfaces that support automotive voltage sensing and cell balancing, following the rule that no solder can be used on any or balancing wires, choosing thermistors with proper electrical isolation ratings, and producing the electrical schematic and wire diagram that would go into the build book. Mechanical handled the creepage and clearance and the routing paths, but we had to make sure every electrical component we chose worked within those mechanical constraints. Our work essentially established the electrical architecture that mechanical and software built on. To meet electrical deliverables, most of our focus this semester was on selecting and validating the electrical components that make up the module. We began with the connectors, since those determine how the CSC boards interface with the cells and sensors. We selected automotive grade connectors that supported crimp terminals instead of solder, had proper voltage ratings, locking features, and pin spacing that aligned with the mechanical routing and clearance requirements. These connector choices also ensured reliable voltage sensing, cell balancing, and CAN communication. Next, we selected the fuses for both the CSC and the serviceable sense line circuits. These fuses had to be sized correctly to protect the cell sense lines during faults, while also meeting automotive ratings and packaging requirements. The mechanical team later confirmed packaging, but we selected the electrical ratings and specifications. For temperature sensing, we standardized on 10K NTC thermistors. We reviewed supplier data sheets to verify that the thermistors had the electrical isolation capability required by the design strategies. Choosing the right thermistor was essential because temperature is one of the key safety indicators monitored by the CSC boards. We also chose the 22 gauge wiring for the cell sense lines and communication lines. This gauge offered the right balance of flexibility, insulation rating, current handling, and compatibility with mechanical routing clips. Once component selection was complete, we created the supporting documentation for the build book, including the electrical schematic, wire diagram, and bill of material. The schematic shows how all the components connect electrically, while the BOM lists every part number, rating, and supplier. These documents ensure mechanical team, software team, and future manufacturing personnel can reference all the same information. Overall, component selection was the core of our hardware work this semester, and it established a safe manufacturable electrical foundation for the entire module.
For my section, I want to walk you through two key deliverables we produced this semester: our 22-pin module harness design and our integration work with mechanical, which you can see in the CAD image. For this table, it shows the 22-pin connector we designed for the battery module. Every single cavity in this connector has a specific job. Pins 1 through 13 are all cell voltage sense lines. C0 to C12, they are the backbone of how the battery pack control module reads individual cells' voltages. Pins 14 through 23 are all temperature sensor circuits. Each temperature node has a signal and a return path, so the BPCM can accurately capture thermal behavior across the module. Everything here uses 22 AWG alpha wire, which meets the voltage insulation and current requirements for low voltage sensing. This sizing also matches what the BMS OEMs typically expect, so it keeps us compliant and easy to integrate later. This table essentially becomes our electrical blueprint. It tells the mechanical team exactly which wires are needed, how many positions a connector must support, and what type of routing space they need to reverse inside the enclosure. Next, this CAD image shows how the mechanical team used our electrical requirements to design the internal harness routing. You can see the green harness bundle traveling across the module, following the exact wire count and connector position we provided. A lot of back and forth went into this. We had to make sure our connector location lined up with their mounting features, that the wire bend radius made safety standards, and that nothing interfered with cooling channels or structural supports. We also confirmed that the harness had clean separation from high voltage zones and the routing wouldn't create strain on the connector during vibration. All of that came from the electrical mechanical collaboration. As the electrical/software team, our job was to define everything the mechanical team needed before they could build the enclosure. What we gave them was the exact wire count, gauge, and signal types, connector part numbers and pinouts, sensing requirements for voltage and temperature, harness bundling and routing constraints, minimum bend radius and clearance requirements, and all the electrical considerations. Mechanical couldn't lock in the physical design until we finalized these electrical needs. Once we handed them this information, they were able to module the internal harness you see in the CAD and the position boards, clips, and protective tubing correctly. So overall, these two deliverables represent a foundation of our module level sensing system and the collaboration required to bring the mechanical and electrical designs together. This work sets us up for the integration next semester when we install the BPCM and start validating the full pack. This semester for electrical and software instrumentation team was all about building that foundation before any hardware could exist. We had to define everything that makes the battery module actually function, the sensing circuits, the connector layout, the routing requirements, and the logic that lives behind it. We designed the entire 22-pin harness, all the cell voltage sense lines, all the thermistor signals and return paths, and the wire sizes that meet the safety and accuracy requirements. That became the electrical blueprint that the mechanical team needed before they could even start shaping the enclosure. They used our pinouts and our signal list to create the CAD routing, the placement of the board, and the protective tubing inside the module. On the software side, we were also building the foundation of MATLAB and Simulink. We mapped out the power up and power down behavior, HPL logic, LOI, and the early monitoring functions. All of that gives us a clear picture of how the battery pack control module needs to behave once we start integrating real hardware. So really everything we did this semester is setting the stage. We built the logic, we built the wiring plan, and we aligned the electrical and mechanical sides so the physical build will actually make sense. Next semester is where everything comes to life. That's when we take all the groundwork we laid and turn it into real hardware. We'll assemble the harness, install the connectors, mount the sensing boards, and integrate the BPCM. All the Simulink modules we've been building will be validated against actual system behavior, and we'll work hands-on with mechanical to make sure the harness fits, the sensors read correctly, and the HV and VLV system stays safe and clean. So in short, this semester was planning the architecture and the rules that define the system. Next semester is the build, where we turn all of our electrical and software work into a working battery module that meets competition requirements.